All right, welcome back, B's and G's. Welcome to the drive-through. Today's lesson in multivariable calculus is vectors in the plane. Hungry? Stop by the deli. Make yourself a sandwich. All right, so you guys are familiar with vectors from your favorite movie. A vector is an element of space that represents magnitude and direction. Okay, what's different between a segment and a vector is that a vector has direction, unlike most of you guys, and a segment just has an endpoints. Okay, so we have to always know what the terminal point is and what the initial point is. So in this little example here, they want to show that PQ, or that vector V, is equivalent to vector U. So if I just sketched vector U, it starts at the origin, it terminates at 3, 2. Again, this is the terminal point. Okay, so we could say that vector PQ, so here's one way to write a vector. Another way is to call it little u, it says. I'm sorry, little v, it says. Okay, and that is going to be, and here's another way to write it, 3, 2. That indicates we go right 3 and up 2 from its original point. Okay, vector u will be, well, I'll show my work here with some subtraction. 4 minus 1, comma, 4 minus 2, which is 3, 2. So I'm going to write vector u in red. Okay, so it's important to understand that even though vector u and vector v have a different location on our plane, they are still equivalent vectors because their components match up. So what we just learned is that the location of a vector is not significant, only its direction and its magnitude. Okay. Okay, find the component form and length, which is magnitude, of vector v that has an initial point 3, -7 and a terminal point -2, 5. Once we find the component form, okay, it's very easy to find the magnitude. So we just use subtraction to find the component form. Let's see, initial point. So I got to do 3 minus a -2, comma, -7 minus 5. It's important that we lead off with the 3 and the -7 because that is our initial point. If we switch those, we would get our direction going backwards. Okay, so our vector would be going the opposite direction of the correct answer. So 3 plus 2 equals 5. -7 minus 5 is -12. So this is the component form, of vector v. All right, so part B, or the second question, says find the length. Well, the length is the same thing as the magnitude, and we write that as that. That means magnitude of v. And to do that, all we got to do is get our Pythagorean, okay? Good old Pythagorean theorem. So we know that 5 and 12 would represent the legs of our triangle. And this is the Janet Jackson of right triangles, the second most famous triangle on Earth, the 5, 12, 13. So the magnitude of V is 13. Okay, moving on up. All right, example 3. Given that V is -2, 5 and W is 3, 4, find each of the following. So W minus V. So this is as easy as it seems. So W minus V is equal to 3, 4 minus -2, comma 5. We just subtract the common components. Okay, so we could also write this as 3 minus negative 2, comma 4 minus 5. Okay, so the solution will be 5, comma negative 1. Now I'd like to show you geometrically what that represents. Okay, so if I just popped an axis right here real quick. Okay, so V is negative 2, comma 5. So left 2, up 5. That is V. All right. W is 3, comma 4. Over 3, up 4. That is W. Okay. When it says W minus V, remember that the orientation or location of these vectors does not matter. So when it says W minus V, let's consider that the same thing as W plus negative V. So if I took my W, which is right here, and I took my V, if you can imagine that this is V, well then minus V is going to be, let's see, that's right. This is minus V. So if I took my W and went right 2 and down 4 and just copied a minus V there, this terminal point should, if we did it right, give us the solution. And indeed it does. That is 5, comma negative 1. All right, we're going to take a pause here. We'll come back and keep going with the lecture. Boom!